Hello everyone. In this video, we're going to talk about how to create an action server. Just like how we created a action client and we used a already created action server, this time we create our own server. And what the server will do is it'll make our turtle sim to rotate inward to in an inward spiral, like shown above. We will do this by creating our own action server and also our own action message. So how this will happen is that we will send in amount of time, and then the turtle sim will rotate in an inward spiral, and while it's rotating it'll give us a feedback whether it's moving or not, and when it's completed it would say that it has completed. So in this video you will learn how to create this server, and also as a bonus you will learn how to create your own action messages. And this creation of action messages is similar to how you can create your own service message or even your own messages in publisher subscriber. So let's dive deep in to build our own server. So in order to create the action server package, it's the same way. We have the launch folder for launch, then folder for source, and then cmake and package xml. First, we'll start with the source file, where I have defined all the header files over here. And as we had discussed, this is the custom interface for an action message which we created, which I'm defining it here. And once again, this custom interface is nothing but it receives time as the goal, and then sends the status as the result, and then sends a string feedback. So this is how we include the custom action server message in this class. And next we also include the geometry messages which we would use to publish the command velocity to the turtlebot. So to start off, first I'll go ahead and explain the class which we define for the action server. So we name it as my action server, and then we define the public aspects of this class, as in we use alias names for move and goal handle. We define the move as the action which we have defined, action message, and then we define the goal handle by using RCL CPP action, and then server goal handle, and then move. Once that's done, we initialize the class and also the super class, which is RCL CPP node. So we do that by doing this, and then we name the node as act server. Once that's done, we define standard placeholders, and then this is where we define um, the action server itself. So you can see that we use this act server and then RCL CPP action create server, and the type of the action message we're using, and then we define the name of this action service. We call it as spiral turtlebot, and then we define the callbacks for different instances. One is to handle the goal, other one is to handle what happens if you cancel it, and the next one is to handle what happens if you when the goal is accepted. So here we also define the publisher the same way, as in we use create publisher, and then we name use the type, and then we name the topic where we're going to publish to and the frequency. Once that's done, we define the private aspects of this class. So what are the private aspects here? We define the shared pointers, which is to the act server. This is the server which we use, and this is the publisher we are going to use. After we define the variables, we define the functions which we are going to use, basically the callback functions which we are going to use in this class. So we start off with RCL CPP action goal response. So this is what happens when you send a goal to this action server. How does that react? So you can see there is RCLCPP action goal ID and then the goal itself. So once a goal is received with a goal ID, what we do in this function is that we say that we received goal, and this is the goal and how long. Uh, Basically, here we are going to send the time duration it's going to spin. And how we accept the goal is by using this type. So we return this RCLCPP action goal response and we name it as accept and execute. We send this accept and execute, which is like an enumeration value, which signifies that you accepted the goal. Once that's done, we go into action cancel response. So this is when you want to cancel an action goal which you have sent. So it's similarly we use goal handle here. Here's when we start using goal handle, and this will be seen throughout in different cases. When we handle it, when we execute it, or when we accept it, we use a goal handle. Um, Here, suppose if this callback is called, you just say that this is cancelled, and then you use this RCLCPP action cancel response and you mention it as accept. So this is how you cancel an action service. And these are the two different aspects, and this is the third aspect where you're going to handle the accepted goal. Once you say you accepted the goal, this is how you would execute it. So you get the goal handle, and then here we start another thread which is parallel to this thread which is running for executing this action server. Yes, we do it so that the executor is not stopped and it keeps uh, aware of like any other action requests goals are coming. So here we say that my action server, we attach this thread to this callback function, which is my action server execute, and we also send in the goal handle, which we are defining here. So when this callback function is executed, we send the goal handle, and using the goal handle, we extract all the necessary details. For example, here you can see that we get the goal using the goal handle, using get goal, and we assign it to goal, and then we create this feedback and we define the type for this feedback as uh, move feedback. So this is the type which we defined here, move user defined interface action move. So we define here move feedback, and then we assign this message and we make it as an reference to this variable. So whatever we change here in this message, it will be flowed back to feedback which we define here, and this feedback is what we name in this action. So here this feedback, so it's the names should match. Once that's done, you first write the value as starting moment, and after that, that's what the value will be written to the feedback. And also you create a result, which is the similar way how you create for feedback, and you create a move which is used for publishing the velocity to the turtle bot. So how we use time and this publishing to be coherent is that we use RCL CPP rate, loop rate. So this can be used to say that this one particular loop will run for 1 second. So you can see that here in this loop condition we set I is less than the goal, the time which we are going to send, and each loop is going to sleep here for that duration. So you can see that loop rate sleep, which would ensure that this one loop would run for 1 second. So first we check if there is any canceling is required. If so, we cancel it. Else we give the message as moving spiral, and we move we feed in the value to x as 1 and then angular z as 0.1 plus I divided by 10. This is to slowly increase the angular z component so that it spirals as it moves along. And then we publish it using the publisher which we created, and also we use the goal handle to publish the feedback that it's been moving. Um, and then we also print that this is the feedback in the terminal. Once this loop is completed, we check if RCL-CPP is okay, if it's all good and running, and then we set the value to the result status as it has finished spinning for this much duration. And then we also set the linear component and angular component to be 0 so that it stops after this whole process is completed. So we then publish that. Once that's done, we use the goal handle and we set in that succeed the result. So this ensures that the whole action server is complete, and then we send that goal succeeded. We print this on the terminal. So this is the entirety of the whole class, what we are going to use for the action server. And this is the main function where you can see you are going to initialize the RCL CPP, and then you initialize the action server, and what you're going to, and then you use the class name over here. Just you create an instance of this class, and here we are creating an executor which is multi-threaded executor so that we can do this aspect, like creating another thread to handle the execution. So that's why we use RCL CPP executor, multi-threaded executor, and we add this action server to this executor, and we spin it until we force it to close. So, and then we define RCL CPP shutdown and return 0. And this is how you define this class and the main function to handle TurtleBot to spin in a spiral direction. In order to create a custom action message, what you do is first you create a package and ensure that the package is dependent to RCL CPP, ROS ideal default generators, and then action messages. So all these are some of the dependencies it should have. And once that's done, the main two components while creating an user-defined interface is that your CMake list and package XML have to be changed a little bit, and then you should have a directory inside this which defines the action. So let's start with defining that action. You can see that there is these dash lines. This is used to differentiate between the goal, the result, and then feedback, which are the three components for an action message. You can see that we are defining an integer for seconds for the time goal which we are sending, and then the string for the result which says it's completed, and then a string for the feedback which says like it's moving or whatever that action is tracking. So this is the second component, which is the CMake list, and here ensure that you have this ROS ideal default generator which is used for defining the interfaces, and you have RCL CPP. All the other things are, if you want, you can have those. And another thing which you need to have is this: you need to have a ROS ideal generate interface and the name of this action. So here you can see that it's inside action and it's called as move.action. So ensure that you have this to generate. You use ROS ideal generate interfaces to generate the action which you have created. Once that's done, you go into the package XML and ensure that you have these three lines defined. The build depend should be there to ROS ideal default generator instead of just depend, which would be the default case. Ensure that you have this, and then you have execute depend as well to ROS ideal default runtime, and then member of group to ROS ideal interface packages. So this three lines is something different when you create a custom action or custom messages, custom service messages. This is like a default template you need to follow. Once this is done, you can then compile this package, and then you would have this package available for your other packages, say action client, action server package, to use in their class, in their source code. And another way to check that you have this action available is to go inside install and go into include and see under the action you have this move.hpp. This is what the program would use to move use the custom interface you have created. So first what we do is we do call on build. As you can see, it builds the package. And once it's done building the package, what we do is we source install. And once it's sourced, the install files, we run the action server node which we have created. And this will start the action node. And once that's done, we will run our turtle sim, source it, and then run turtle sim node. So now you can see the turtle sim is active. Now to get the turtlebot to move around, we give a ROS2 command. How we do that is like first we define ROS2 action, send goal, and then we specify the goal. So how do we do that? We name the action server, spiral turtlebot, and then we define the type of the action server and then tell how much seconds it's going to go. That's the goal. So when we give the goal as 20 seconds, as you can see, it starts to move around in the spiral for 20 seconds. It says whether it received the goal, whether it's constantly moving. It's saying it's publishing the feedback. That means it's doing what it's supposed to do. And also it says whether it completed the goal successfully or not. So this is how the action server is implemented. And that's it. And this is how you would create an action server and also an action message. And you can use this concept to create your own action servers to do very complicated tasks. As in, even the path planning in Move It happens through actions. And this is a very powerful concept. You can use it throughout. Thanks for watching and subscribe to get weekly robotics content.